with our discussion? All right. Okay, so let me try to share my screen with you. Again, I'm not the host. Okay.
Hocam bir ara bir session düzenleyebilir miyiz acaba? Bu kontrol sistemleri üzerine yeni ne gelişmeler var, neler yapılıyor? Öyle bir şansımız olabilir mi acaba sizden öğrenmek?
Yani bir sohbet toplantısı yapabiliriz. Ben de istiyordum aslında. Hem genel fikirlerinizi almak için. Ama hani ne kadar hani kontrol sistemleri alanındaki son gelişmeler konusunda ne kadar bilgilendirebilirim sizi. Hani orası belki tartışılır, bilmiyorum ama tabii ki yani bir sohbet yapabiliriz. İsterseniz yılbaşından sonra önümüzdeki haftanın ikinci yarısında bir ara ayarlayalım. Olur mu? Ha, bu arada dün size söylemeyi unuttum arkadaşlar. Ama asistanlarımız yazmışlar. Ben aslında derste söyleyecektim. Konuştuk onlarla. Sanıyorum ki cumartesi mi? Hafta sonu bir ekstra, hani mazeretsiz kaçıranlar için bir ekstra quiz düzenleyecekler. Onu da tekrardan hatırlatmış olayım. Oldu mu? Yani quiz kaçıranlar için bir ekstra quiz yapacağız.
Hocam mazeretsiz mi dediniz?
Mazeretsiz, evet. Yani herhangi bir sebebi olabilir. Tamam?
Anladım.
Yani hani bir şekilde kaçırdıysanız, çözemediyseniz vesaire katılabilirsiniz. Okay? Alright. So let's start back our discussion. Okay, so remember that we started talking about distributed systems, and as opposed to lumped parameter systems, where the variables of interest are not only a function of time, but they are also a function of space or some other variable. Okay, so the example that we will discuss is a heat conduction process, where in fact this is one of our experiments in the lab, where a metal rod, which is a good heat conductor, is basically wrapped within an insulator, so that you can assume that there is no loss of heat from the boundaries of the rod, but the end points of the rod are open. Okay, and one end point is used to inject heat energy in the object, and another end is where heat energy is escaping from the other side. Okay, so let's remember what we talked about. Okay, we basically said that heat energy, not heat energy, the temperature distribution inside the temperature distribution inside the solid is a function of both time, which is our time variable t, and space, which in this case is a single variable x, because we only have one dimension, and we assume that distribution is homogeneous with respect to a constant x. Okay, so there is no sideways distribution, but in general, obviously, if you think about this problem, this space variable can be multidimensional. It may be 2 or 3 dimensional space variable, but time variable obviously is scalar. Okay, now this distribution is determined by the inflow of heat, which is basically the heat flow density, that is given by Q omega at 0, and the outflow, let me take it this way, and the outflow, which is flow density Q omega L. L is basically the maximum value of the space variable, okay? It signifies the other end of the rod, basically. We make certain assumptions to simplify the problem, okay? We assume fixed, fixed parameters, certain parameters. One is the heat conduction coefficient. We will see what that is. Heat conduction coefficient is fixed. So that means essentially, so the material density is fixed. So we assume that heat is basically moving within the rod, facing essentially homogeneous parameters. Okay, there is no density differences, there is no material property differences. Specific heat capacity is also constant. Remember, specific heat capacity is essentially the material property that signifies how much heat a unit volume of the material can store. Okay? Okay, so these parameters are fixed along the rod. Okay? Now the way we will treat this problem, as I said, is to consider a thin slice within the material. And this kind of problems are common, for example, in electromagnetics, in when you take your calculus courses. It's basically one of the fundamental tools in engineering is to define any infinitesimal, very small element and try to treat that element with the physical properties, some relations of that and then by using that infinitesimal element and the integral calculus, basically you can extend that infinitesimal element to derive equations of what's going to happen throughout the entire body or throughout the entire process. Okay, so we will consider a thin slice of material within the rod of length dx. Now we will write the heat balance equation for that element. Heat balance equation for that element. Basically what it says is that, remember what this element does, right? This is an element of thickness dx, very thin slice. What's happening is that this slice resides at a distance x from the origin. Okay, and what's happening is that at this element you have an inflow of heat q omega at x, and there is an outflow of heat energy q omega x plus dx. Okay, because you have thickness dx. So in this case, if we write our conservation law, remember we had the basic property that any accumulation has to be the result of inflow minus outflow, be it a fluid or energy or whatever. In this case, it's the heat energy. Okay, so from our lumped parameter model, you would remember that accumulation is basically related with the change in temperature with respect to time, and it also relates with how much heat capacity the material has. In this case, we have the volume of this section, right? This is A times dx, which is the volume. times the density of the material times the specific heat basically determines the capacity of the material to store heat. That determines the change of temperature with respect to time. Now the reason we have this strange delta is that this is a partial differential. That means in fact the temperature is a function of two variables, x and t, but in this case we are only taking the derivative with respect to time. Okay, obviously we can also take the derivative with respect to space as well because of the presence of the two variables. Okay, so this whole thing is our accumulation part, and that has to be equal to the inflow minus the outflow, and that is also determined by the area times the flow densities, because you have a flow density, which means flow per unit area, and you have a total area, so there will be a total inflow. So Q omega at x minus Q omega x plus dx. Okay, so that's the inflow minus outflow part. Okay. Now we can obviously we can write this as let's continue with this, a times dx times rho times cp dt xt over delta t del t. That has to be equal to basically we have over here minus a times, this is also part of a derivative, this is a difference, and if I divide this with respect to delta x, which is over here it's the dx, right? This becomes a derivative actually, provided that we have an infinitesimally small section of the material. Okay, so we can write this as a derivative dq omega over dx, but also because this is only a difference, we need to cancel out this dx. Okay, so this is dx cancels out, there is only delta q omega remaining. All right. Why the minus sign? Because remember the definition of the derivative is a variable plus the delta minus the variable at, so it's q omega x plus dx minus q omega x is actually the part of the derivative, so we have a minus sign. Okay, so we have some cancellations over here. So we have a being cancelled, dx is being cancelled. Okay, so that gives us essentially rho times cp dt xt over dt is equal to minus del q omega over del x. Okay. Now, also, we want to write this heat flow in terms of the temperature. Now, there is something called a Fourier law for thermal conduction. This is actually related with, remember, if we had a boundary for the lumped parameter model, let's say there is material A and B, okay, and there is a temperature T1 and a temperature T2, because of there will be heat flow when there is temperature difference. For example, if we consider the heat flow as Q, we know that we also have this Q being equal to some constant, which is a constant of thermal conductivity, and let me just erase this part. Okay, area and the temperature difference. Okay, we already knew that. Now this has a counterpart in the continuous version, and that's the Fourier law for thermal conduction, which states that the flow, the heat flow, is a constant lambda minus a constant lambda times the derivative of the temperature with respect to the space. So the flow is a function of how much change there is temperature with respect to the space variable. If there is no change, if it's constant, the derivative is zero, and therefore there will be no heat flow. But if there is a gradient, if there is a temperature change with respect to the x variable, necessarily there will be a flow of heat. Okay, which is kind of this was the lumped version, and this is the continuous version. Okay, and later on here, lambda is kind of related with alpha, and we will see the relationship in a minute. But essentially, lambda is the coefficient of thermal conductivity. Okay. So let me put this part within this equation. Okay. So we will express Q omega in terms of the Fourier law for thermal conduction. So essentially what I'm going to get, and I will divide both sides by this constant. So del Txt over del T is equal to plus lambda over rho Cp times del square Txt over del x square. Okay, so this is essentially a partial differential equation. Okay, over here we give this term a special name. We call it A, which is lambda over rho times Cp, and this is called the factor of heat conductivity. You can see that this A is highly related with the alpha that we had defined before as the heat transfer coefficient. Okay. So remember, for our regular lumped parameter systems, one way of deriving a mathematical model was to basically derive the differential equation, and that's a way of putting the mathematical model. Okay, differential equation is one mathematical model format, and we later on transform that into the Laplace domain to have transfer functions as another way of representing the system if it was linear and if it had zero initial conditions. Now this equation is a partial differential equation. This is a mathematical model of this process of heat conduction. Okay, so let's make that a note here. So this is a partial differential equation. Partial differential equation. Equation model of heat conduction in a solid body. Now, this is obviously much more difficult to deal with as compared to an ordinary differential equation because we have a variable that is both a function of time and space, and the governing equation has derivatives with respect to those both of these variables. On top, it's a second order differential equation, right? You have a second order derivative of the temperature with respect to the space variable. Okay. Now, maybe you would remember from your differential equation courses, but the solution of this kind of equation requires boundary conditions which are kind of the initial conditions for the x variable. And also it requires initial conditions, which are the variables, which are the initial conditions for the time variable. Okay, so let's also move on to the discussion of that. Okay, the solution, another note. The solution requires boundary conditions for the space variable x at x is equal to 0 and x is equal to L, which are the beginning and ending portion, and initial conditions for the time variable at obviously the initial time t is equal to 0. Let me give you an example, or let me explain what I mean by that. The boundary conditions obviously are temperature at, let me see, what was my first variable? It was the space variable, right? So temperature at the first boundary is T0 of t. Interesting, is still a function of time, right? So you fix the space variable for the first boundary at x is equal to 0, but this boundary condition in fact is a function of time, or can be a function of time, because we just fix one of the variables. The other variable is still free. Okay. Similarly, at x is equal to L, still you will have basically a boundary condition, which is a function again. Okay. So if we think about our rod, which is inside insulators, like this, right? What we are saying is that in terms of the boundary conditions, okay, this determines what's happening here at this boundary, and this one determines what's happening at this boundary over here. And similarly, the initial condition is basically the other way around. You have the x variable free, but the time variable fixed. So this is going to be t0 of x. Okay, so is defined for the entire space variable. So that means what we are saying is that this initial condition now at the initial time actually has to specify a function of x. That means something is going to be the initial condition within the rod, but potentially the temperature might be different at different locations in the rod initially. Okay, so that is the initial condition.
Hocam bir şey sorabilir miyim?
Sure, go ahead.
Şimdi matematiksel olarak sadece düşünürsek herhangi iki noktayı veya herhangi bir zaman anını almamız yeterli değil mi? Yani mesela T0 olmasa da atıyorum T1 anında olsa bu da bizim için denklemi çözmeye yeterli olmaz mı?
Tabii ki, ama genelde şöyle o zaman mesela zamanı eğer 0 almazsanız o zaman non-zero bir andan geriye doğru denklemleri çözmek çok daha zor olabilir. Dolayısıyla herhangi bir andaki değeri almak initial condition olarak o andan sonrası için çözümü gene mümkün kılar tabii ki. Ama öncesi için çözmek için denklemlerin modifiye edilmesi gerekir.
Anladım.
Dolayısıyla bir zorluk yaratır yani. Ama temelde dediğiniz doğru. Sonuçta biz göreceğiz zaten. Hani differential equation derslerinde de gördünüz. Sonuçta biz bu denklemi çözmeye çalışırken bir takım unknown variable'lar çıkıyor. Ve o unknown variable'ları bulabilmek için biz initial condition'ları veya boundary condition'ları kullanıyoruz. Dediğiniz gibi herhangi bir yerde veya herhangi bir anda specify edilmesi onları çözmeyi kolaylaştırır. Denklemi elde etmeyi kolaylaştırır. Ama gene sonuçta oradan geriye doğru bu sefer o denklemi çözmeniz gerekir. Eğer sıfırdan itibaren mesela ne olduğunu bulmak istiyorsanız.
Evet.
Tamam. Başka soru var mı? So let me put that observation as a note again. Boundary conditions conditions are a function of time and initial conditions are a function of space. Okay, space obviously is a generic term. In some applications, this other variable may be something different than the space variable, but in this case, for this problem, it is actually the space variable. Okay. Now let's take a look at let's take first a look at how we can derive the steady state solution of this equation. Okay, so let's say if we allow infinite time, would this system be converging into a distribution in space where time becomes unimportant? Everything becomes stable with respect to time, so there is no change with respect to time anymore. But there is still something remaining, which is a change with respect to the space variable. Okay, this is called a steady state. It's called steady state because it happens as time goes to infinity. It converges to a steady state condition. Okay. It's like an equilibrium point for an ordinary differential equation, right? What's an equilibrium point? An equilibrium point is that all change in the variable of interest with respect to time becomes zero, and therefore you arrive at an equilibrium. Now, an equilibrium for a partial differential equation, in fact, is a function with respect to the remaining space variable. Okay, so steady state condition can be derived as follows. So we assume, first of all, that in order to arrive at a steady state, obviously we should impose that nothing is happening with respect to time at the boundaries. Okay, we assume constant steady state boundary temperatures. Obviously, these are like an input to the system, right? If you have a time varying boundary temperature, you cannot achieve steady state because you're constantly exciting the system with different temperatures from the boundaries. Okay, so let's assume that T0 SS and TL SS are given to us. Okay, now we have to define this steady state in a way similar to we have defined the equilibrium. Okay, steady state implies that we have del t xt with respect to the time is necessarily equal to 0. Okay, so we assume that there is no change with respect to time, and obviously this eliminates the kind of the derivative with respect to time. Okay, so the partial differential equation becomes an ordinary differential equation. Okay, so the left hand side of that equation becomes 0 because the derivative with respect to time is equal to 0. We have a times del square. Now I'm calling this the steady state solution, xt, with respect to dx square. Okay, and a is cancelled because of the 0 on the other side, and a is a constant, so we can just divide both sides by a. Okay, still an ordinary differential equation. Fortunately, it's a very simple ordinary differential equation because of just the derivative term being there. Okay, how I can deal with this is that I can integrate both sides. So when I integrate 0, I get a constant. Okay, because the derivative of a constant is equal to 0. The integral of, and I'm going to write this part in an interesting way. So there is a second order derivative over here. Okay, and the integration is with respect to the x variable, obviously. So I have d over dx of d TSS x over dx times dx. Okay, so this part is what was already there, and this dx is actually the integration variable of our integral. Okay, so these dx's cancel out, so this is an integral of a delta. So what this gives us is basically our derivative, dTSSX over dx. Okay, so we got rid of one of the derivatives, but we got a constant on the left hand side. Okay, so we will do this again. So integrate again. So now I'm integrating a constant. So this is this will give me this C1 will become C1x, because this term, when you take the derivative with respect to x, it's going to result in the constant C1 plus another constant coming from 0. Now this time again the same goes here, integral of d TSSX over dx times dx. Dx's cancel out. So you get essentially TSS of x. So we get from this is that in fact the steady state temperature with respect to the space variable is a linear function, C1x plus C2. Okay, so it's not a constant. It will vary linearly from the left boundary to the right boundary, where C1 and C2 are to be determined. We don't know yet their values. Okay. Any questions so far? So how we're gonna find them? You guys tell me.
T0 ve TL verin.
We will use the boundary conditions at x is equal to 0 and x is equal to L in order to find what C1 and C2 is. But let's do that the next time we meet. Okay? Is there any questions so far? Soru var mı arkadaşlar? So, as an exercise, determine C1 and C2 by evaluating TSSX at x is equal to 0 and x is equal to L. Okay? Peki arkadaşlar, soru var mı? O zaman teşekkür ederim. Haftaya görüşmek üzere. Görüşürüz arkadaşlar. Yeni yılınızı kutluyorum hepinizin ben de. İyi seneler diliyorum. Umarım 2020 biraz daha sakin bir sene olacak.
Umarım.